Equilibrium is a state of balance between opposing forces or actions that is either static or dynamic. Static, as in a body acted on by forces whose resultant is zero. Dynamic, as in a reversible chemical reaction when the rates of reaction in both directions are equal. There are two conditions for equilibrium. 1. The net external forces must be acting on a body must be zero, and 2. The net external torque must be zero. Statics is concerned with the calculation of forces acting on and within structures that are in equilibrium. The basic principles of statics were discovered early. The fundamentals of levers, inclined planes, and other principles were used by early civilizations in the construction of huge structures like pyramids. Archimedes introduced the concept of lever equilibrium as early as 287 to 212 before Christ, while Leonardo da Vinci conceptualized moments in relation to equilibrium in the latter part of the 15th century. The center of mass or center of gravity is a useful concept when dealing with equilibrium problems. The center of gravity of a body is the point where its entire weight may be assumed to be concentrated. The body's center of gravity and center of mass are identical in the assumption that the body is small enough for gravity not to vary over its extent. The center of gravity may be inside or outside the body. For a circular plate, the center of gravity is at the center and is inside it. For the traditional donut, the center of gravity is also at the center but outside the donut. For a regular shaped object, the center of gravity is its geometric center. If the object is irregular in shape, the center of gravity may be determined experimentally, either by balancing or using the plumb line method. Whether a body is stable or unstable depends upon the location of its center of gravity. In general, an object will be stable if a plumb line drawn from its center of gravity falls within its base. This is called the condition of stability. Some objects are easier to knock over than others, even though they will not tip over themselves. In this sense, the greater the weight, the broader the base, and the lower the center of gravity, the greater is the stability of the object.
Newton's first law of motion, applied to translation and rotation, gives so-called conditions for equilibrium. The first condition for equilibrium states that an object that has no net force acting on it is said to be in translational equilibrium. In equation form, force being a vector quantity may be resolved into its horizontal and vertical components. Thus, the first condition for equilibrium may be equivalently exposed in a necessary condition for a body to be in rotational equilibrium is that the sum of the torques about any pivot must be zero. The condition is known as the second condition for equilibrium. If the resultant of the forces acting on a body is not zero, the addition of another forces, called the equilibrant, is needed to balance the resultant to produce translational equilibrium. This force is equal in magnitude to the resultant force but oppositely directed. If the resultant of the forces acting on a body is zero, then any of the forces is equilibrant of the other forces. For example, 8 boys are equally spaced about a pushball and each exerts a force upon it toward the center. As shown, each boy in positions 1, 3, and 7 exerts a force of 17 Newton, and the rest of the boys exert 15 Newton each. What force is needed to keep the ball at rest? Solutions. From the figure, we can see that the forces exerted at the following positions cancel each other out. 2 and 6, 3 and 7, 4 and 8. The net force that will accelerate the ball is the resultant of the forces exerted at positions 1 and 5, which is 20 Newton rest. To keep the ball at rest, a force of 20 Newton will be added to 50 Newton, which is in position 5. To make it 70 Newton and to keep the ball at rest, ease must be applied.
This time, I'm going to discuss about a particle versus rigid body. So what is particle? Particle is a mass of negligible size, allows maximum simplification when the shape or size of the body don't matter. And rigid body is a body of fixed, unformable size, allows substantial simplification when the changes of the shape of the body don't matter. So what is different between particle and rigid body? Basically, particle have non-deforming mass and rigid body have non-deforming mass with shape or size. Rigid body analysis required when length or size of the object must considered, including rotation and torque. Particle versus rigid body. Distinction has to be made whether the object being acted upon by a system of force is a particle or rigid body. A particle may be considered as a point mass. Forces acting on a point mass are concurrent, and hence there is no concern for rotation. Only the first condition of the equilibrium must be satisfied because of the absence of forces that would cause rotation or torque. A rigid body is an extended body in space that does not change size and shape. Most often, the lines of action of forces acting on a rigid body do not pass through a common point. Hence, the body may be equal to zero. Thus, for rigid body to be in equilibrium, the condition must be satisfied.
A demo vendor carries a 1.5 long light plank over his shoulder. At the ends of the plank are two buckets weighing 40 N and 60 N respectively. A. Find the value of force F exerted by his shoulder. Neglect the weight of the plank. B. Where should he support the plank for F to be balanced horizontally? Solution. Let us draw the free body diagram of the plank. A. Applying the first condition for equilibrium. F minus 40 N minus 60 N is equals to 0. F is equals to 100 N. B. Let X be the distance from end A to the point and support of the shoulder. We may solve for X by letting end A as the point. The summation of this of A is equals to X times negative 100 Newton sin 90 degrees plus 1.5 meter times 40 Newton sin 90 degrees is equals to 0. So the X is equals to 0.6 m from end A. So the Tahoe vendor should support the plank 0.6 meter away from end A or 0.9 away from end B.
The motion of heavenly bodies obey Kepler's law of elementary motion and Newton's law of the universal gravitation. The force from the planets and the sun must be proportionate to the product of their mass, according to Kepler's third law and Newton's third law. Inferring from Kepler's law and Newton's law that the force that keeps the planet in their orbit by continuously changing their velocity so that they followed an elliptical path.
On the other hand, it was said that Isaac Newton discovered the physical law that governs an apple falling from the tree to the ground. He realized that the apple is attracted to Earth in the same way that the Earth is attracted to the apple. He added that this attraction between Earth and the apple must also hold true for the planets, Earth's moon, the sun, and for every object in the universe. With this idea, Newton formulated the law of universal gravitation.
Kepler's first law is one of the three laws that describe the motion of a planet in the solar system. Kepler's first law, also known as the law of orbits, states that the orbit of a planet around the sun is an ellipse, with the sun
at one of the two foci of the ellipse. This means that the planet will not move in a perfect circle around the Sun, but rather in an oval-shaped path. It states that all planets move in elliptical orbits around the Sun, with the Sun located at one of the two foci of the ellipse. The shape of the ellipse is determined by the gravitational force of the Sun and the velocity of the planet as it moves through space. The law explains that the planet's distance from the Sun varies throughout its orbits, with its closest approach being referred to as its perihelion, and its farthest point being referred to as its aphelion. An example of Kepler's first law in action is the orbit of the planet Earth around the Sun. The Earth's orbit is not a perfect circle, but rather an ellipse. This is why the Earth is closer to the Sun at some points in its orbit perihelion and the farther away at others aphelion. Despite this variation in distance, the Earth always follows an elliptical path around the Sun, with the Sun located at one of the two foci of the ellipse. Also, an ellipse can easily be constructed using a pencil, two tacks, a string, a sheet of paper, and a piece of cardboard. Tack the sheet of paper to the cardboard using the two tacks, then tie the string into a loop and wrap the loop around the two tacks. Take your pencil and pull the string until the pencil and two tacks make a triangle. Then, begin to trace out the path with the pencil, keeping the string wrapped tightly around the tacks. The resulting shape will be an ellipse.
Hi guys, at this point we will be discussing all about Kepler's second law of planetary motion, which is also called the law of equal areas. So before anything else, let's have first some brief explanation about the origin of Kepler's second law of planetary motion, which is also called the law of equal areas.
Have you ever wondered how the Sun and planets are arranged in the solar system?
Thanks to the meticulous astronomical observation of his colleague and his employer Tycho Brahe, Johannes Kepler was able to test several rival hypotheses for how the Sun and planets are arranged in the solar system, eventually leading to his three laws of planetary motion: law of ellipses, law of equal areas, harmonic law or law of periods. And now, let's focus on Kepler's second law of planetary motion,
which says that if you draw a line from the Sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as the equal area in equal time law. And this law works because Mars doesn't move a constant velocity. It speeds up as the closer it gets to the Sun. So if Mars is approaching perihelion, the point in the orbit nearest to the Sun, it's traveling faster than if it's aphelion, the point that is farthest away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slowly. Either way, the area sweep out in a fixed amount of time is the same.
The third law is called the harmonic law or the law of periods, which can be stated as the square of the sidereal periods of the planets are directly proportional to the cubes of their mean distance from the Sun. The ratio of the square of the periods of any two planets revolving around the Sun is equal to the ratio of cubes of their mean distance from the Sun. What does the third law means? Kepler's third law means how long a planet takes to go around the Sun, which is its period, is related to the planet's mean distance from the Sun. The square of the period divided by the cube of the mean distance is equal to a constant and for every planet, no matter what its period or distance. Mathematically, this can be expressed as p squared over r squared is equal to k, where k is a constant of proportionality. This law applies to all planets in the solar system as well as to other celestial objects orbiting a central body. We will be deriving Kepler's third law, so to derive this, we have a following situation. We have a planet of mass lowercase m, which is orbiting around the Sun, which has a mass capital M. The radius of the orbit, or the average radius of this orbit, is given by r. The gravitational force, we know that the magnitude of the force is going to be Gm divided by r squared, where uppercase M is the mass of the Sun, lowercase m is the mass of the planet, and r squared will be the average radius of its orbit. It will equal to mv squared divided by r. Now, we can clearly see that we need some cancellations. We will cancel all the masses. We can also cancel out one of those r. Important reminder is, because the planet is moving in a circle, we can say that the velocity of the planet will be equal to the distance traveled divided by the times, because it's moving at a constant velocity. So the distance traveled will just be the circumference of the circle, which is 2 pi r, and divided by the amount of time it takes for the planet to move around its orbit. Let's square that as well. V squared is going to equal 4 pi squared, r squared divided by t squared. Let's rewrite the following equation. Gm divided by r equal to v squared, but instead of v squared, we will write this expression. So, 4 pi squared r squared divided by t squared. We will be arranging this expression. So, t squared gm is going to equal to 4 pi squared and r cubed. The final step would be just to rearrange for the t squared. So, t squared will be equal to 4 pi squared divided by gm multiplied by r cubed. And that's it. That's how we derive the third law of planetary motion.